Rebuttal to Bev and the Try Thinking on the Level crew, round 3.3, perpendicular to a circle. This started back in my round 3 video where I posed a pair of math challenges. What is the slope of a parabola, and what is the perpendicular slope to this parabola? Bev punted and scrolled right to the answer key. It's a shame because it's a fun little exercise, discovering the slope of a curve where the slope is constantly changing. So I recorded a follow-up video, round 3.1, where I derived the difference quotient from the slope of a secant line, find it for the parabola, and then finally take the limit, resulting in the answer of 2x for the slope of the y equals x squared parabola. To illustrate the limit of the difference quotient, I even made a spreadsheet, showing the values of the slope approach the true value of the slope as h approaches 0. I also included the negative reciprocal slope for the perpendicular to a graph. And then, for fun, I also repeated the process for the top half of a circle, because this entire exercise was inspired by the On the Level folks insisting you can't find a perpendicular to a circle or to any other curve. To show that 2x is indeed the slope of the graph, and also that negative 1 over 2x was the slope of the perpendicular, I graphed them on graph paper. And it turns out that you can, in fact, graph the perpendicular to a slope. Our good friend Saragaki had something to say about this procedure. He wrote, "Oh no, he called the straight line connecting the 2 points a secant." Sorry, Saragaki, but the difference quotient is literally defined as the slope of the secant line. If you had taken calculus, you'd know this, but even if not, you can simply follow along with my derivation and it should all be clear. It's always ironic when people feel they've caught me making a mistake, when in reality, womp womp. Once we algebraically find the slope, also defined as rise over run, we could find the perpendicular slope by finding the negative reciprocal. There is no tangent to the curve needed. But here's Saragaki again, claiming that I'm not finding the perpendicular to the curve, but rather the perpendicular to the tangent. Ouch. So I'm going to go through the process again, this time with the equation for a circle, and we'll see if there's a tangent anywhere in my steps. Before we begin, it's helpful to recall what David Dunning said in his TED lesson on the Dunning-Kruger effect. On average, people tend to rate themselves better than most in disciplines ranging from health, leadership skills, ethics, and beyond. What's particularly interesting is that those with the least ability are often the most likely to overrate their skills to the greatest extent. It's amusing how many times folks without a strong grounding in math will make very forceful mathematical assertions which are dead wrong. The example under consideration is their insistence that you cannot construct a perpendicular to a curve or a circle. I have a few ideas. So here's my modest theory about why they say things like this. The Earth can be approximated as a sphere. Spherical geometry can be performed on the surface of a sphere. Therefore, some folks must deny spherical geometry exists. The cross-section of a sphere is a circle. Plane geometry can be performed with this circle, including drawing perpendiculars to it, otherwise known as real-world verticals. Therefore, some folks must deny that perpendiculars can be drawn to a circle. Due to their denials in number 3 and number 6, they conclude that the Earth cannot be a globe. But whenever I mention the globe, their silly, ironic response is, "'Tis globe." So let's go through the process of mathematically finding a perpendicular to a circle with a bonus addition to my spreadsheet. We'll start with the Pythagorean theorem and a right triangle. So here we have a squared plus b squared equals c squared, and if we treat that c is the radius to a circle, we can figure out a new formula for a circle. And so if we have a fixed value r, the set of all xy coordinates that are r units from the origin form a circle. Now if we take the radius equal to 1 and the center is 0, 0, we have x squared plus y squared equals 1. That is our equation for a unit circle centered at the origin. And so if we solve this for y, we get plus or minus the square root of 1 minus x squared. Now we're just going to take the top half of this to make it a function. Top half of this circle, and then in function form, that's f of x is the square root of 1 minus x squared. All right. So we're going to find the slope of this. Again, we're going to take 2 points, x comma f of x and x plus h comma f of x plus h to put in to find the difference quotient. All right, so the x's cancel out in the denominator, and we are left with our difference quotient. Now the difference quotient, we can plug in the function. This is, again, the top half of a circle, and we get this. Now this looks fairly ugly, and it has h in the denominator. We really want to get rid of h, so we could do a clever little step, and that is to multiply this numerator by the conjugate. All right, so that's the sum of those square roots. We're multiplying the conjugate of the numerator, and it's a little trick. If you have a minus b and you multiply it by a plus b, the product of the conjugates gives us a squared minus b squared. So essentially the numerator is the difference of squares. The square root signs disappear. All right, and so there's our denominator. Again, h is now out front. And we can cancel some things in the numerator, factor out an h in the numerator, and then cancel those h's out. So this is going to be our difference quotient. All right. Now we're going to take the limit. Now the limit of the difference quotient is equal to the slope of the function. So if we take the limit of this difference quotient, those h terms are going to go to 0, which means they're going to disappear from our final equation. Now it turns out that the denominator is repeated, so we can put a 2 in front of that. All right, and then the 2's cancel out, and this gives us our slope of the function, but we're interested in the perpendicular slope. So there is our perpendicular slope, square root of 1 minus x squared all over x. And what we're going to do is we're going to test this out with a sample point, and I'm just going to arbitrarily pick the point at 45 degrees. So we're going to test what the perpendicular slope to the circle is at 45 degrees. So this line in red is what we should be getting back out. They should tell us that it's a slope of 1. But our input is going to be this x value. Now, if you remember from geometry, a 45, 45, 90 right triangle, we have a special right triangle. That x value is going to be root 2 over 2, same as the y value. All right. So we are going to substitute x equals root 2 over 2 into our formula, the formula that we had just discovered. All right. So the perpendicular slope is the square root of 1 minus x squared all over x. We're going to substitute in root 2 over 2. And for x, and it gets a little bit obnoxious, this is a what we call a complex fraction, where your numerator and or denominator are also fractions. So what we're going to do is, since we have we're dividing by a fraction, we can simply multiply by the reciprocal. All right. And then after a number of steps, we find that the slope is in fact equal to 1. All right. So what does this mean? The slope of the perpendicular to the circle at a 45-degree angle is 1. We confirmed that from what we were expecting. And so here it is drawn out a little more precisely. All right, this red line is the perpendicular to the circle, and it does in fact have a slope of 1 over 1, or a slope of 1. All right. So what we're going to do is we're going to try this with a couple more points, and we're going to use our spreadsheet to streamline the process a little bit. So here's our equation of a circle. It's actually just a quarter circle, but it's a unit circle centered at the origin. Again, this is the perpendicular to the curve, the square root of 1 minus x squared all over x. All right. Now we're going to try this with several different points. All right. This and this is 25 squares. 25 squares equals 1. So this is not 25. It's still 1, but each one of these squares is 1/25 of a unit. All right. So this x point is actually 22 squares over. So it's 22 25ths. All right, because again, this is still a unit circle. It's a circle with radius 1. So what we're going to do is we're going to turn to our spreadsheet, and we're going to plug in 0.88, all right, which is the equivalent of 22 25ths. And let's do that now. So you'll remember that this is our spreadsheet, slope of a curved function. I've got some instructions. It starts off with the parabola, and it also has a page on the semicircle. All right, so again, this is the top half of a circle. It is a function. So we are going to plug in 0.88. That was the value we had determined. And down here, this is the slope of the perpendicular line. It is a 0.53974282221, probably goes on. And the problem is, how are we going to graph that slope? That slope is not very easy to graph. So I've added something to the spreadsheet. I've added the graph paper slope assistant. So if we click here, what we're going to do is we have our choices. We can type in a slope. For example, I could type in, a slope of 3.21, right? And then what it'll do is it will find a whole bunch of possible close slopes, meaning slopes with either the numerator or the denominator being 1 through 12, and it gives us some best, its best approximation. And you just want to look for ones that have a very, very low error. Now, we want to get the slope from the semicircle, and so we can just copy it straight over using this pull-down menu. We want the perpendicular to the semicircle. So when I click there, it gets that 0.539742, etc., etc. And as we scan, again, we want to look at the ones in green. We see a couple pretty good ones. 6/11 is pretty good. That's 1% off. 8/15 is 1% off. But 7/13, if you look at that, the actual slope was 7/12.97. And 7/13 is a really good approximation. So we're going to graph 7/13 on our paper. So on our graph paper, if we were to count rise 7, run 13, we're going to run off the paper. So what we're going to do instead is we're going to count -7 over -13. So we're going to count still a slope of 7/13, but we're going to go in the negative direction. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now this slope is not exact. All right, the slope is not exact, but it will be very close. And it does appear to be perpendicular to the circle. Let's try another point. How about this point? And if we come down to the x-axis, it has a slope, or I'm sorry, it has an x value of exactly 0.6. So turning back to our spreadsheet, we're going to plug in 0.6. So we're going to go back to the semicircle tab, and we want a x value of 0.6. And that gives us a perpendicular slope of 1.3 repeating. Again, if we go back to the graph paper slope assistant, we find that a perfect slope is 4/3. And there's a bunch of repetitious, 8/6 and just a multiple of 4/3. So we're going to graph a slope of 4/3 from here. And we can actually go in several directions. We can go rise 4, 1, 2, 3, 4, run 3, 1, 2, 3. I always tell my students to graph multiple increments of the slope. Rise 4, 1, 2, 3, 4, run 3. And we can actually go in the opposite direction. We can actually, not only do 4/3, but we can do a -4 over -3. So 1, 2, 3, -4, and then 1, 2, -3. I can repeat that. 1, 2, 3, 4, 1, 2, 3. I think that's enough. And again, that is perpendicular to the circle. Let's try another one. This one, it's 7 squares in on the x-axis. So if you count that out, it's actually 7/25. 7 squares out of 25. So 7/25, and that simplifies to 0.28. Let's plug in 0.28 into our spreadsheet. So go to the semicircle tab. We're going to type in 0.28, and it gives us a slope of 3.42857. All right, so we're looking at a pretty good one, and it looks like there's only one, and this one is exact. All the other ones are approximate. We got a couple pretty good ones, like things that round to 0%, but this one is exactly 0. This is 24/7. 24/7 is the perpendicular slope. So let's see, and again, if I counted up, I would not be able to do 24/7. I would run off my graph paper. So I'm going to count down 24 squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and I'm going to count left 7 squares. 1, 2, 3, 4, 5, 6, 7. So this is very interesting. It turns out that the slope is actually the same. It maps out the same as the radius. So I'm just going to draw it as a radius. And again, this radius is perpendicular to the circle. So that is one of the things that we had talked about before, is what angle does a radius make with the circumference? The radius of a circle is perpendicular to the circumference. I love how, when taking things back to first principles, mathematical ideas can reinforce and validate other ideas from different directions. So no, Saragaki, we are not just finding the perpendicular to the tangent. To answer the question of if we can draw a perpendicular to a circle or another curve, the answer is yes. It's called the normal to the curve. And if you have a curved surface, it's called a surface normal, or a normal vector, as shown here. Returning to the slope of a function, are there any practical applications? All students taking a calculus-based physics course know the answer to this one. Let's draw the position graph of a simple tennis ball that's being thrown vertically upwards. And if we graph the position, the height of the tennis ball above your hand over time, we're going to get a nice parabola. All right, so it comes up steeply. It's going at a fast velocity. It slows down and then comes back down with another fast velocity. Now, we are not throwing the tennis ball in a parabola. We're throwing the tennis ball straight up. So h is simply the height in meters above our hand. Now, before we continue, what I want to do is I just want to mark a couple key points. Now, if we were to try to find the slope of this position graph at any given point, you'll see that the slope is constantly changing. It does have a slope of 0 here, and then it's got a slightly negative, and then ever more increasing, and then here's a strong negative. So it turns out that the slope graph will look like this. It starts off at a very high slope, and then it comes down to 0, and then it goes to a negative slope. And basically, the change in height over time is known as velocity. In this case, in SI units, it would be meters per second. Now, here's a good one. How do we refer to the change in velocity over time? Again, velocity is meters per second, and then we're going to do per second. So meters per second would be the acceleration graph. Now, if you notice the slope, this slope is constant. It is a constant negative slope. So that will look like this. And if we were to actually measure this in the real world, this is negative 9.8 meters per second squared, otherwise known as the acceleration due to density and buoyancy. Did Euclid know any of this? Of course not. He was writing about 25 centuries ago. Euclid was a giant, but the study of mathematics didn't end with him. Isaac Newton was a towering English scientist, but he did not take all the credit for the developments himself. He wrote, "If I have seen further, it is by standing upon the shoulders of giants." Interesting, Newton is credited as being the co-founder of calculus. and it's hard to find a calculus text that doesn't include analytic geometry. There's no shame in admitting you don't know, but it is folly to argue against knowledgeable people from your position of ignorance. You may fool people who know as little as you, but you will look foolish to everyone else. As usual, I want to express my thanks to my channel members. Your support is appreciated. When commenting on this or any other video on my channel, please show kindness to others. Bye!